Curiosity rover has found some exciting new clues adding to the case for life on Mars. It discovered molecules that actually came from ancient microbial life, which are old enough to show that such life, if it ever existed, might have left behind some clues that are still around today. The new findings come from a bit of rock that Curiosity analyzed way back in 2020. It used its onboard lab equipment to release gaseous molecules from the sample and identify them. Earthbound analyses have now confirmed that the rock, which came from a part of the Martian mountain called Mount Sharp that was once covered with water, held 21 different carbon-containing molecules. NASA says that that's the most diverse collection of Martian organic molecules ever found on the red planet. In fact, 7 of those molecules had never even been detected on Mars before, including nitrogen heterocycles, which are considered to be precursors to RNA and DNA, 2 nucleic acids that are key to genetic information. Another exciting discovery was benzothiophene, a carbon and sulfur-bearing molecule that's been found in many meteorites. These meteorites, along with the organic molecules within them, are thought by some scientists to have seeded prebiotic chemistry across the early solar system. Finding organic molecules is promising in and of itself because these represent some of the basic building blocks that make life as we know it possible. Still, they don't necessarily mean that life did evolve on Mars, but because the bedrock is estimated to date back about 3.5 billion years, which is around when Mars had liquid water on its surface, the fact that Curiosity got any chemistry results at all is very exciting. Scientists have no way of knowing whether these organic molecules were created by biologic or geologic processes. Either path is possible, but their discovery renewed confirmation that ancient Mars had the right chemistry to support life. Given the high levels of radiation on Mars stemming from its thin atmosphere, scientists weren't actually sure they'd even be able to detect chemical signatures from that ancient window of potential habitability. Captured by the multispectral imager instrument on NASA's Psyche mission, this view shows the large double-ring crater Huygens, which is about 290 miles in diameter, and the surrounding heavily cratered southern highlands near 15 degrees south latitude. It is the 5th largest recognizable impact crater on Mars, and the largest one with a near-intact rim. The various colors in this dramatic scene are likely due to differences in the compositional properties of dust, sand, and bedrock in this ancient terrain. Multiple branch channels are also visible in the observation. The existence of these channels is strong evidence that much water once flowed on the surface of the planet, where simple organisms may have once lived where water once was. Carbonates were also discovered in a crater on the rim of Huygens. The impact on the rim exposed material that had been dug up from the impact that created hydrogens. These minerals represent further evidence that Mars once had a thicker carbon dioxide atmosphere with abundant moisture, as carbonates of these kinds only form when there is much water. The Mars Reconnaissance Orbiter has also detected clay minerals in the vicinity, and the carbonates were found near the clay minerals. Both of these minerals form in wet environments. It is believed that billions of years ago Mars was much warmer and wetter. At that time, carbonates would have formed from water and the carbon dioxide-rich atmosphere. Later, the deposits of carbonate would have been buried, but the double impact has now exposed the minerals. Earth also has vast carbonate deposits in the form of limestone, a type of carbonate sedimentary rock which is the main source of the material lime. The Curiosity rover recently drilled a sample from a new region inside Gale Crater with features that could reveal whether Mars' subsurface once provided an environment suitable for life. New images from the rover show the first close-up views of a region scientists had previously observed only from orbit. The images and data being collected are already raising new questions about how the Martian surface was changing billions of years ago. The red planet once had rivers, lakes, and possibly an ocean. Although scientists aren't sure why, its water eventually dried up and the planet transformed into the chilly desert it is today. By the time Curiosity's current location formed, the long-lived lakes were gone in Gale Crater, but water was still percolating under the surface. The rover found dramatic evidence of that groundwater when it encountered crisscrossing low ridges, some just a few inches tall, arranged in what geologists call a boxwork pattern. The bedrock below these ridges likely formed when groundwater trickling through the rock left behind minerals that accumulated in those cracks and fissures, hardening and becoming cement-like. Eons of sandblasting by Martian wind wore away the rock but not the minerals, revealing networks of resistant ridges within. The ridges Curiosity has seen so far look a bit like a crumbling curb. The boxwork patterns stretch across miles of a layer on Mount Sharp, a 3-mile-tall mountain whose foothills the rover has been climbing since 2014. Intriguingly, boxwork patterns haven't been spotted anywhere else on the mountain, either by Curiosity or orbiters passing overhead. A big mystery is why the ridges were hardened into these big patterns and why only here. As Curiosity drives on, it will be studying the ridges and mineral cements to make sure of how they formed. Important to the boxwork patterns' history is the part of the mountain where they're found. Mount Sharp consists of multiple layers, each of which formed during different eras of ancient Martian climate. Curiosity essentially time travels as it ascends from the oldest to youngest layers, searching for signs of water and environments that could have supported ancient microbial life. The rover is currently exploring a layer with an abundance of salty minerals called magnesium sulfates, which form as water dries up. Their presence here suggests this layer emerged as the climate became drier. Remarkably, the boxwork patterns show that even in the midst of this drying, water was still present underground, creating changes seen today. In this observation, many craters in the mid-latitudes of Mars are partially filled with deposits that have been interpreted to be ice-rich. It is believed that the deposits had formed at an earlier but relatively recent time when Mars' orbital parameters were different and allowed ice to condense and deposit in these locations. The ice is covered by dust layers protecting it from sublimating away. The ice deposits are probably no older than a few million years, which is recent in geological terms. However, observation shows that these deposits have been affected by even more recent movement of the crust that clearly postdates the ice deposits because it is cutting through them. A wider view allows the tracing of this crustal movement or fault, and observe it also affecting the crater wall and the area surrounding it. This observation indicates that Mars' interior is still, or at least, until recently was warm enough to sustain such activity.